I just want to do some housekeeping before I start, which is if you look at section 2.4, it's basically all the topics we have discussed so far related to tensor operations. Like, for example, it talks about addition, magnification, transpose, tensor products, contraction, contracted multiplication, all the things that we discussed 2 or 3 lectures ago. So what I want you to do is review section 2.4 completely. It covers all the topics that we have discussed. Maybe I didn't discuss it in exact same order as it appears in the book, but it's all in there in section 2.4. Okay. Before section 2.4, there are sections that talk about vector operations and definition of tensor. Since you are all graduate students, I assume you know vectors. So I didn't spend special time discussing vectors. We discussed a lot about what is a tensor, and we did a lot of discussion around that, coordinate transformations. So this section 2.4, 2.5, and 2.6, these 3 sections are the ones that I'll be covering in the exam. As far as in the first exam, in this unit, you just need to be expecting questions in these 3 sections only, because these 3 sections use concepts from previous sections. So if you are attending or answering these problems, it means you know the entire topic. That am I being clear? For the exam, you need to be ready about these 3 sections. Firstly. And last lecture, we talked about how to derive eigenvalues and eigenvectors for a given matrix or a tensor. That is covered in section 2.5.3. Okay, so the last lecture's material goes with this section. Today and Tuesday, I hope to wrap up section 2.5 and 2.6. 2.5 is sort of an easy list of properties that we are going to see. It may not take up entirely today's lecture, so we'll try to get through. And 2.6 tensor fields is essentially your gradient, divergence, curl, those Laplacian, those sort of operators, how to derive them in tensor notation. So that we'll discuss. Okay. Sorry. So I mentioned about a additional assignment where you could write a computer program which will calculate the eigenvalues and eigenvectors of a 3 by 3 matrix. We all agreed that we would try it, right? So yes, right? Yes. So you remember there is a project in this course worth 25%. So what I thought is, let's keep the homework 1 at the same level of 5%, take some percentage of the project and include it with the include it or give it for this assignment. So now if the project is initially worth 25, maybe I'll reduce it to 20 and make this programming assignment worth 5%, which is a reasonable thing because programming is much easier than doing an entire project. So your 5% here is more or less guaranteed because all you have to do is write a program. Then, so in every unit, that is every unit, if an interesting scope for programming assignment comes up, I'm going to chip away a percentage from the project and make you these special assignments so you could do the learning while keep getting the credit for it. So 5% credit for writing this program. How does that sound? Is it too much, too easy, too difficult? I want some thoughts.
So 5% only for this one, or
5% for writing this program and 5% for homework 1. Risky. Okay. How can we de-risk it? What do you think?
They're both due a week from the day, right?
We can make them due on different days so that you get time to work. Suppose we can stick to the schedule. On February 25th, the homework 1 is due. Maybe we'll do a week later, the program is due. How about that? 1 week to write the program, additional time. Sounds good? Sounds like a good deal for you? All right. So 5% for homework 1 remains the same. 5% for the programming assignment to write a program for eigenvalues and eigenvector calculation. And I'll give you some pointers or hints on how to do this. Okay, it's not that I'll just leave you to fend for yourself. Okay. All right. Tonight, my homework is I'm going to catch up in posting the recordings. I'm going to find recordings from last semester that I can share with you on related topics, because there was that one lecture where audio wasn't there. And I will repost the homework file with these details about the project, the computer programming, as well as the regular homework. Okay, all that I'll do tonight. All right, that said, let's get into the topic. Anything not clear? Anybody wants to get some clarification? These three, I mean, this is of course included in this. 2.4, 2.5, 2.6. That's what those topics will only appear as questions, but indirectly they will involve concepts from previous sections. So, okay. All right. So I want to start with this properties of tensors. The first property we are going to see 2.5.1, orthogonal tensors. What is an orthogonal tensor? So a second order tensor Q, a second order tensor Q is orthogonal if for any vectors A and B, QA dot QB is also equal to A dot B. Oops. This basically means what is A dot B in whatever we know about vectors? What do we know about A dot B? Yeah, A1 B1 plus A2 B2 plus A. That is the expression. What does it represent? Of course, it's the dot product. What does the dot product represent? If they're orthogonal. So if you have a vector A and you have another vector B, geometrically, what is A dot B? A dot B is the component of A along B, or the other way, right? What we are saying here is Q is a second order tensor. It is like a operation. It could be rotation, stretching, some kind of operation. If you operate Q on A and the result of this is a vector, and you operate Q on B with the result of which is a vector, the dot product of those vectors is same as A dot B. Or in other words, geometrically, Q preserves the magnitude of A, or magnitude of the vector on which it operates. That is, can you think of a transformation which preserves length? What is tensile? Sorry? Rotation. Classic example, rotation preserves length, it only changes orientation. If you apply linear displacement, you are by definition changing length. If you apply compression and twist, you are also changing length. But if you apply pure rotation, that is an example of something that doesn't change the length of the object or body, or geometrically speaking, it preserves the magnitude of the vector. And this Q Q will preserve the magnitude. Q is orthogonal if Q multiplied by its transpose or Q transpose multiplied by Q is equal to the identity tensor. If this condition is satisfied, Q is an orthogonal tensor. You can also say if Q is orthogonal, this will be satisfied. You can say it either way. Okay. So you can write Q is orthogonal and put a double arrow sign. It goes both ways. Q times Q transpose is I. Q transpose times Q is also I. What this basically means is Q inverse is equal to Q transpose. When is the product of two matrices equal to the identity? If one is the inverse of the other. So you can write Q transpose should also be equal to Q inverse. Only then this will be true. So the corollary of this condition is that Q is such a matrix whose transpose is also its inverse. So far we know several operations regarding matrices, right? First is computing determinant. You know about determinant. If you are not already comfortable, or second we saw computing eigenvalues and eigendirections. If you're not already comfortable, you should be able to compute the inverse of a matrix. Be frank, do you know what is the formula for inverse? Do you recall?
By determinant.
So if say Q is a matrix, inverse of Q is equal to 1 over determinant of Q multiplied by what is called as the cofactor matrix C11, 12, 13, 21, 22, 23, 31, 32, 33, the cofactor matrix transpose. What is cofactor matrix? C11 or Cij is minus 1 power I plus j times the subdeterminant. I don't remember the formula for it, but I'll just give an example. Suppose you are considering C11. C11 is minus 1 power 1 plus 1 multiplied by what will be the elements here? A22, A23, A32, A33. So you can fill out the remaining entries and that will be how you will compute inverse. An orthogonal matrix is one whose inverse is just the transpose of it. The reason I'm listing these properties is whenever you find that a certain transformation or deformation is orthogonal in nature, a variety of simplifications will follow from there, such as inverse equal to transpose. Okay. So kindly make a note of this somewhere where you can reach it easily because we'll often compute one of these three quantities. Section 2.5.2. Symmetric and anti-symmetric tensor. I think we might have already seen this. Symmetric and anti-symmetric tensors. So if you have Q, you can write it Qij EI, EJ. Q transpose is QJI, EI, EJ. If QIJ or QJI equal to Qij, this would make it a symmetric tensor. If Qji equal to minus Qij, that would make the tensor or matrix antisymmetric, which we saw before. But one more additional thing we are going to see today. Can I erase the middle part? Middle part. Yeah. So having these definitions, you could always do one thing, which is if T, if let's say T equals Tij, Ei, Ej is any tensor. We're not saying it is symmetric or antisymmetric or anything. Then the tensor with components Tij plus Tji by 2, Ei, Ej is symmetric. True. It's easy to prove it. Can you just tell me how this will be always a symmetric tensor?
If T, I and J is still the same, right?
Yeah, if you swap I and J, that is, if you suppose we call this, let's say A, that is, this is Aij. What is Aji? Aji is replace I with J and J with I, Tji plus Tij plus divided by 2, which is also equal to Aij. So any tensor can be written as, or using the components, you can construct a symmetric tensor. Okay, consider the other combination. Tij minus Tji divided by 2. Ei, Ej, and we'll call this B. This tensor whose components are constructed as Tij minus Tji divided by 2 is an antisymmetric tensor. Again, prove. Very easy to prove this. Same type of argument. You would replace I with J and you will end up with Bji being equal to minus of Bij. So this is a symmetric tensor. This is an antisymmetric tensor. So if you take Tij, can I write this as Tij plus Tji divided by 2 plus Tij minus Tji divided by 2. Can I write it this way? Can I just take a tensor and write it as first this component plus this component? I mean, if you take a closer look, this is nothing but Tij. All I did was to split the one into two halves, add and subtract Tji. So you can say this is T, which is equal to Aij plus Bij, Ei, Ej. What does this statement mean? Any tensor,
And we have combination of antisymmetric and symmetric.
you can even say directly not combination, but the sum can be expressed as the sum of a symmetric tensor and an antisymmetric tensor. Antisymmetric tensor. Okay. Any tensor can be expressed as the sum of a symmetric and an antisymmetric tensor. That's the result. So I'll write it in words here. Any tensor can be expressed as the sum of a symmetric and an anti-symmetric tensor. The reason I'm stating this is we will use these type of mathematical manipulations when we do the theorems and derivations. Okay. I'm going to erase this side. I see. Okay. So any tensor can be expressed like this, and A is the symmetric part and B is the anti-symmetric part, symmetric part. Okay. An interesting property is I want you to calculate what is A double contraction B. That is, this is short form for Aij, Ei, Ej, dot, or we have to do, yeah, we'll write dot like colon, Ek, B, KL, Ek, EL. This is Aij, BKL, EI, EJ dot EK, and then there is also dot EL. What is EJ dot EK? Delta JK. Delta JK. And then you have, so this is Aij, BKL, delta JK, because that is a scalar. And then I have EI dot EL, which is delta IL. So I have Aij, BKL, delta JK, delta IL. This is A. I'll replace L with I and K with J. Aij, BJI. Can you compute what is Aij, BJI, knowing Aij is right here and BJI is right here? What is BJI? Minus Bij. So this is Aij minus Bij. What is Aij? Tij plus Tji divided by 2. Tij minus Tji divided by 2. I'll tell you the answer. I want you to get to it. This is equal to 0. How? All right. So I'm going to take a hint the book gives. We are here, right? So yeah, we are here. So we'll write this is Aij, Bij with a negative sign. And what is Bij? What is Bij? Minus Aij times Tij minus Tji divided by 2. Okay, so you have 1/2, which is common, minus Aij Tij plus Aij Tji. Okay, with me so far? I just did multiplication. Okay, so let's continue here. 1/2 minus Aij Tij plus, I'll write this as Aji Tji. Is that correct? I'm replacing this with Aji. Is that okay? That is a symmetric tensor, right? So it's okay. Look at this term. This is I and J, I and J. I is a dummy index, J is a dummy index. This is Ji, Ji. So I can, if it's not too confusing to you, I can say replace the dummy indices. Instead of calling it J, start calling it I. Instead of calling it I, start calling it J. If that's not confusing to you, I can write this is nothing but Aij Tij, which is same as this. That's one way to think about it. But if you are kind of like upset by that, I can say start calling J as some let's say M, and start calling I as N. Now you can rewrite the same thing in terms of M and N. Then drop M, replace M with I and N with J, you will end up with the same result. So that you take one step in between, not to confuse yourself, then you rename it one more time.
Do that whenever.
You can do it here because this is already a summation. That is, this by itself is a sum. The two indices are repeating, which make it a dummy index. Suppose one of them is K. K is not a dummy index here. You don't sum over K. It's there. It will take values, whatever you assign it. It's not a sum. In that case, you can't do this operation. You can't do it whenever you want. You can do it whenever there is a dummy index and an implied summation. Okay. It's like saying this is a number. This is also a number. The only thing that different between them is the name you given for the counter. That's why this is okay. Okay. So these two are the same, which makes A double inner product equal to 0. That is, the antisymmetric and symmetric parts at, when you contract them, they become 0. So we are still talking about the properties of symmetric and antisymmetric tensor. We started with the definition. We then saw the possibility that any tensor can be expressed as the sum of a symmetric and an antisymmetric part. The double inner product or double contraction of the antisymmetric and symmetric and antisymmetric parts is 0. The last result we are going to see is if B is the antisymmetric part, antisymmetric tensor, then there exists a vector, we'll call it W, for which A dot, sorry, B dot A is equal to W cross A for any vector A. For any vector A in that space. That is, the progression would be, if you know B is an antisymmetric tensor, then it will have this property and you can solve for W. That is, from here, W can be obtained from this relation. You would obtain W as Wk is equal to minus 1/2 epsilon ijk times ak. Prove this. I'm going to let you try it at home, that is, try it later. Your exam questions, at least if I suppose, hypothetically speaking, if there is an exam only on unit 1, let's say there is 3 problems. I told you 3 sections, right? In one of the problems is going to be determining eigenvalues. One of the problems is going to be proving one of these tensor relations. And the third problem is going to be related to tensor fields. When we have the first exam, probably there are going to be 2 units. So the number of questions per unit will reduce. But these 3 topics, you should be able to answer any question, any homework problem, any relation to be proved, you should be able to do that. That's what I'm hoping to see. Right? So if I say, the exam question could read something like this. B is an antisymmetric tensor, and then there exists a vector W. Prove that W is equal to this. This is a question. So you should be able to prove it. So using index notation, doing this sort of manipulation, making arguments about dummy indices, these are the kind of things you should work on. You may ask me, why should I do all this? Which is the wrong time to ask that question. If you ask that question, you shouldn't be in this class, because in this class you signed up to learn tensors, and this is part of learning tensors. So you should not ask, why should I do this at this stage? So section 2.5.3, eigenvalues or principal values and directions, we already saw that. We have finished that unit, so I'm not going to go over it again. I urge you to read through section 2.5.3. I will, however, just recap. I will recap one thing, which is so let's say G is any tensor. How do we compute eigenvalues and eigenvectors? Can you tell me the steps? What's the first step? Set up the characteristic equation, which is determinant of G minus lambda I equal to 0. Set up the characteristic equation. Okay. Step 2. To set up the equation, you can make use of what are called the principal invariants. This is minus lambda cubed plus I1g lambda squared minus I2g lambda plus I3g equal to 0. This is equation 2.74, where I1g is equal to trace of G or nothing but GII. I2g is equal to the trace of G inverse multiplied by the determinant of G, and I3g is equal to the determinant of G. Remember the program that you need to build. Whenever you are given a tensor, you will be given 9 numbers. Computing this from that matrix is really straightforward. Sum of diagonal elements. Trace of the inverse matrix multiplied by its determinant, and then determinant itself. You got 3 numbers, plug them in, you have a cubic equation. So if you are thinking of a program, first step is computing these. Then you have your cubic equation, which you will solve for lambda 1, lambda 2, lambda 3. You just need to use a polynomial solver. You can use the built-in functions in MATLAB or Python or whatever language you are going to use. So you will get 3 values. 50% of the work is done. Eigenvalues are ready. So 2.5% of the credit is already locked in. Now we need to determine eigenvectors. What is an eigenvector? An eigenvector is G dot X equal to lambda alpha times X. That is, for each eigenvalue, you will have a unique eigenvector which will obey this relationship. Okay, so you have to set up 3 equations in 3 unknowns, but they won't be distinct equations. They will be like linearly dependent. Okay, so what you need to figure out is how to get eigenvectors or x1, x2, x3 for alpha, where alpha can take values 1, 2, and 3 for 3 directions basically. This is the part you need to really figure out and put it down as a program. This is the real hard part. Okay. So once you have the eigenvectors, this part is over. There is any tensor G. Any tensor G can be, any tensor G will yield 3 mutually orthogonal eigenvectors. This is the program you are asked to compute. Okay. So last lecture, I said something wrong. I want to make that correction here. I said any vector G or any tensor can be represented as alpha equals 1 to 3, lambda alpha. We'll call this, actually, I think I used the symbol gamma. Last lecture I said this, okay? Gamma alpha, gamma alpha. I said this last lecture. It is not entirely correct. Any tensor G cannot be expressed like this. Any symmetric tensor can be expressed like this. I basically left out the word mentioning that any symmetric tensor can be expressed like this. So I should write any symmetric tensor can be expressed as, and this expression is called spectral representation of S. So I will also write make correction to nodes from 211. That is, on Tuesday I said that I should have said any symmetric tensor, not any tensor. So if you write a symmetric tensor S, that is equal to Sij Ei Ej, and you know it's symmetric because Sji is equal to Sij. This is also equal to lambda 1, lambda 2, lambda 3. 0, 0, 0. Actually, I shouldn't write like this. I want to write this is equal to alpha equals 1 to 3, lambda alpha, gamma alpha, gamma alpha. This is like writing lambda 1, gamma 1, gamma 1, plus lambda 2, gamma 2, gamma 2, plus lambda 3, gamma 3, gamma 3. In Cartesian coordinate system, this representation would look like this: S11, 12, 13. This is going to be 2, 1, but I also write that as 12, 22, 23, 13, 23, 33. This is in Cartesian. Okay. This matrix can also be represented as lambda1, lambda2, lambda3 as a diagonal matrix with other elements being 0, and this is called principal coordinates. So in this representation, can you compute what are these quantities? The I1s. What is I1s? What are the principal invariants?
Delta.
Trace of the tensor. Trace is nothing but sum of the eigenvalue. What is I2? Trace of the inverse tensor. What is the trace of this tensor? Sorry, what is the inverse of this tensor? The inverse of this tensor, S inverse, is nothing but 1 over lambda 2, lambda 3, 1 over lambda 1, lambda 3, 1 over, yeah, no, wait, no. So you have to replace this with lambda 2, lambda 3 and divide by the determinant. So you'll just get again 1 over lambda 1, 1 over lambda 1 inverse 0, 0, 0 lambda 2 inverse 0, 0, 0 lambda 3 inverse. Assuming in general one of lambdas is not 0. So what is the trace of the inverse? That would be 1 over lambda 1 plus 1 over lambda 2 plus 1 over lambda 3 multiplied by determinant, which is lambda 1, lambda 2, lambda 3. So you can write this as lambda 2, lambda 3 plus lambda 1, lambda 3 plus lambda 1, lambda 2. And I3s, nothing but lambda 1, lambda 2, lambda 3 determinant. So again, I'll repeat, you missed it. Last lecture, I mistakenly said any tensor G can be expressed in spectral form. That is incorrect. What is correct is any symmetric tensor can be expressed in this form. And if you do this, you can get this representation. The proof for this is given in page 50 and 51. Proof in pages 50 and 51. So I really apologize for misspeaking last time. Sorry. This is sort of completing section 2.5.3. Then we want to go on to the next one. Cayley, Hamilton theorem. What is Cayley-Hamilton theorem? Let's see. more than proving the theorem, we are going to use the theorem for our benefit, like as a tool. First of all, what is the theorem without proof? The Cayley-Hamilton theorem states that any second order tensor, we'll name it or label it T, whose components are real on R3, meaning the components are real numbers, satisfies its own characteristic equation. This is the theorem. First of all, let's see what that statement means. So if you have a tensor T, what is its characteristic equation? Minus lambda cube plus I1T lambda squared minus I2T lambda plus I3T equal to 0. Am I correct with the sign? Yeah, plus minus alternately. Okay. So this is the characteristic equation. If you read the theorem, it says any tensor satisfies its own characteristic equation, meaning instead of lambda, if you substitute the tensor T itself, it will satisfy or add up to 0. That's what the theorem says. And we will accept the theorem. We will accept without worrying about proof, trusting that it is true. What this means is you can write minus T cube plus I1T T squared minus I2T times T plus I3T equal to 0. So if you first look at this equation, what observations can you make? What is the right side? The scalar. T cube T squared I2 times T plus I3 equal to 0. So we have written it in a form such that every term should be a scalar and then it adds up to 0. Okay. So if you look at the, like I said, this has a utility, right? The utility is, actually I should have written I3T times identity tensor equal to 0, not just I3T. Okay. So the utility is you can write T cube equal to I1T times T squared minus I2T times T. I'm writing this out. T cube equal to I1T multiplied by T squared minus I2T times T plus I3T times I. This is easy. I. This is also straightforward because you know the tensor T. You are given that tensor. You can compute T squared and you can use this equation to compute T cube. So it's a way to calculate higher powers of a tensor. So if you want T cube for some reason, or if you want T to the fourth for some reason, you can take T and then multiply it with T cube, which is this expression. You can get higher powers, T power 5, T power 6, and so on. So Cayley-Hamilton theorem, which we accept without proof, is just a way to calculate higher order powers of a tensor. Okay. After you have done this calculation, T3 is a matrix. It has 9 numbers. This is just one multiplication operation rather than multiplying 3 matrices in a row. So if you are writing a program, all you have to have is a subroutine to do matrix multiplication, that is multiply 2 matrices, 2 3 by 3 matrices. And with that subroutine, you will be able to calculate any power of T as desired. Okay. So this is in section 2.5.4. Last idea or property that we are seeing here is called the quadratic form. Quadratic form of a symmetric tensor. A symmetric tensor. So we saw that previously S, a symmetric second order tensor, can be written in spectral form using the eigenvectors as basis vectors. The key idea here is these directions are derived from the eigenvalues of that tensor itself. If you want to think of if R is a tensor such that R squared equal to S. S squared is easy to think of, but what we are really asking you to think of is a tensor R whose squared is S. It's like in complex algebra when you first learned, I squared is a number which, or I is a number which when squared gives you -1. It's a definition like that when we say R is a tensor which when squared gives you S. Okay. If S can be written in spectral form in this way, then R is nothing but sigma alpha equals 1 to 3 square root of lambda alpha gamma alpha gamma alpha. That is, R has eigenvalues lambda 1 square root, lambda 2 square root, and lambda 3 square root, and the same eigenvectors gamma 1, gamma 2, gamma 3. Again, keeping the proof. We need the result, so we don't worry about the proof here. We skip the proof. The reason we are going to we define this, you can almost call it like a square root tensor. It's like saying, not literally, it's almost like saying R equals square root of S. Okay, we'll need this. That's why we are doing it. So if you have a symmetric tensor, you can write it in spectral form, and you can immediately jump to the tensor R, which is R, which satisfies R squared equal to S, and write R as just square root of alpha and the same basis vectors. That's the result here. Okay. So S, if S or sorry, if R exists, then S is called positive definite. Suppose you get eigenvalues which are all negative, for example, then square root of that negative value doesn't exist. So which means R doesn't exist. If the eigenvalues are positive, then R exists, which makes S positive definite. Okay. So I have about 25 minutes. I just have one minor concept to mention. And instead of starting section 2.6, we'll try to do some of the homework problems, like at least discuss the homework related to what we saw today. So when is your homework due? Just checking. 25th at the beginning of lecture, bring a paper copy. Some of you asked me, can I submit a PDF copy? It should be literally a scanned copy of your handwritten work. I don't want typed up work. If it's a PDF of that is scanned of your paper writing, I will take it. But don't give me a typed up material. Okay, is that clear? Or paper is simplest. Just bring it and I'll be able to grade it. All right. Section 2.5.6. Isotropic tensors. What is isotropic? Have you heard of that word? In what context? Okay, I'll try to remind you. Anybody else wants to say something? What is isotropic? Anybody working on composites? Composite materials? No, yes. No. Can you give me an example of a composite material?
Reinforced concrete.
Reinforced concrete. How is it a composite? The steel, right? You have two phases. You can think of lot of materials that are composite. Composite, the word means composed of several things. So if you take your clothing will have multiple types of fibers in them. It's a composite material. So if you suppose have a material that is made up of layers of material A, material B stacked to each other. So layer A, B, A, B, A, B, or A, B, C, A, B, C, A, B, C. So if you take a certain width of that material, if you are in a certain zone, you are in material A. If you take a step forward, you are still in material A. But if you take a step sideward, you jump into material B. Or you take one more step, you jump into C. In other words, the properties of this material are uniform in one direction, but non-uniform in the lateral direction. Or in other words, there is a directional dependence to the properties of that material. Suppose you think of deformation. You take a point that is in material A. Suppose material A is iron. And material B, the next layer, is some kind of plastic. Just for example, You obviously know a point in a metal will obviously respond differently to a tensile stress than a point inside plastic. In other words, if a tensor has properties or components which don't change when coordinates are changed, when coordinate transformations are done, it is an isotropic tensor. A change in coordinates, that is, instead of going in this direction, suppose you start going in the lateral direction, if the properties change, it is not a isotropic, or in other words, it is anisotropic. So mathematically speaking, it's very simple to write. An isotropic tensor is one whose components are unchanged by coordinate transformation. Components are unchanged by coordinate transformation. When is that possible? It's usually possible. So suppose you have Tij and you have done a coordinate transformation. We say it's unchanged, right? It's like saying Tij is also equal to Tij, that is in the new coordinate system versus the old or current coordinate system. What is Tij prime? Tij prime, you can write this is Q alpha I, Q beta j, T alpha beta. Remember 2 lectures ago we saw what is the definition of a tensor. You will write that in terms of the 2 directions that are getting transformed, Ei prime, Ej prime, and E alpha, E beta are the current coordinate system. This just happens to be equal to Tij. That's what definition says. Okay. So examples. Number 1, scalars. Any quantity that is a scalar has no relevance to direction. You know this fact from a very long time. Mass, density, things like that. So then vectors. When does a vector doesn't change with respect to coordinate transformation? A vector by definition will change. The only vector that doesn't change is when if all the components are zeros. Zero vector. Second order tensor. They don't change only if they are diagonal matrices, or they are defined only by the diagonal elements. Wait, not only diagonal elements, it has to be basically a scalar times identity matrix. And I'll give you the proof for that. So we first write Tij is equal to Q alpha I, Q beta j, T alpha beta. This is the starting point for what is the transformation? That is, this is Tij prime, which is also equal to Tij. It's the starting point. The book uses a proof wherein they make some special choices for Q. Like for example, they say if Q equal to 0, 0, minus 1, minus 1, 0, 0, and 0, 1, 0. I mean, it's just a little bit out there for me to say, oh, if Q is this, then it can be easily proved. But instead of that, what I'm going to ask you is, if a transformation looks like this, just look at it and say what kind of a transformation is this. what is this operation really? What kind of an operation is this? It's, if you look at the first row, it says x1, x2 remain the same, but the third value, third component is flipped in sign. That's like a reflection. So if you had a point here, I'm almost saying the x and y coordinates are not going to change, but the z coordinate is going to become the negative of this. This is like almost like saying a rotation 180 degrees about z axis or third axis. This is the same. It is 180 degrees about x axis. What is this then? About the y axis, but there is no, it's not 180 degrees, it's like 360 degrees. So that you come back to the same value. Okay, so this is in effect a matrix or a transformation that represents pure rotation. Okay, what we are essentially saying is any pure rotation operation, or there's not any pure rotation operations can in some cases lead you to isotropic tensors. Okay. We'll leave it here because if we talk about the proof, it's quite complicated, and even the book says that, and just says that without proof. So we just okay. What should you learn from this section? That is section 2.5. We saw a lot of properties. If you really think about it, let me summarize. We saw what are orthogonal tensors. We saw what are symmetric and anti-symmetric tensors. Okay, and we saw the properties of symmetric tensor. That is when we saw principal values and directions. We saw spectral representation, which is essentially a property of symmetric tensors only. 2.5.4, symmetric representation of symmetric tensors. 2.5.4, we saw the Cayley-Hamilton theorem. Hamilton theorem for computing higher order powers. And then section 5. Section 5, quadratic form. Quadratic form, which is R squared equal to S, and then isotropic tensors. What do I want you to know from this topic? If I give you an expression, say, given that S is a symmetric tensor, prove the following. What it generally will involve is one of these 6 properties that you need to use and go through the operation. The fact that some tensor is symmetric actually allows you so many types of simplifications that you should be able to use while doing proofs. This is what I expect you to know. In unit 2, when we do deformation tensor, we will use these properties. Okay, any deformation in general is not symmetric, but we will use result 2 to express it as a symmetric deformation and a antisymmetric deformation. Okay, so that is why we painstakingly see these properties, which they may not look very intuitive right now, but as the physics comes in, slowly things will fall in place. So, like I said, I'm not going to start section 2.6 now. We have 10 minutes. Let's see if we can pick anything from the homework and try to work on it. So last lecture, I discussed section problem 2.14. I hope you will be able to do that. It's basically eigenvalue calculation. Look at problem 2.13. I don't know if that's in the homework or not, but it's still interesting. Consider the dyad AA constructed from the vector A. Write out the components of D in matrix form. D is given as A, where A can be written as AI, EI. Write out the components of D in matrix form. So this is AI, AJ, EI, EJ. So what will be the matrix form? A1 squared, A1, A2, A2, I'm sorry, A1, A3, A2, A1, which is same as A1, A2, A2 squared, A2, A3. Compute the principal invariance of D, that is, compute I1D, I2D, I3D. And the eigenvalues of D. Compute lambda 1D, lambda 2D, lambda 3. If you start with this principal invariance, you can at least use it in the cubic equation, right? The characteristic equation is nothing but minus lambda cube plus I1D lambda squared minus I2D lambda plus I3D equal to 0. This book uses a lot of symbolic problems. Like they make you work with in terms of these abstract symbols. What I am hoping to do is to make you write those computer programs where you will work with real numbers. So when you try to look at a deformation, it's a formula, but at the end of the day, you can substitute numbers and get 9 real numbers and work with those. That's what the numerical component is supposed to do. This is a little boring even to me to work with these symbols and keep doing algebraic manipulation. But if you understand the principle, I hope you will implement it in the computer. All right. What is I1D? Do you remember the formula? So this is exam. You are asked to compute I1D. You don't know, you forgot, but you can still look up because it's an open book exam. I'm not going to make you memorize these formulas. For a symmetric tensor, is there any benefit? Is there any simplification? So I1D is trace of D, trace of D, which is A1 squared plus A2 squared plus A3 squared. I2D is trace of D inverse times determinant of G, or they also do it slightly differently. Half trace of D squared minus trace of D squared minus trace of D squared.
Just trace.
Trace is sum of diagonal elements. So you'll have to compute what is trace of D, which is easy, but you also have to compute what is D squared. So that's basically matrix multiplication. You have A1 squared, A1, so you have this, you'll have to multiply this with itself. So it's going to be a lot of multiplication. So if you just multiply first row with first column. What is first column? A1 squared, A1, A2, A3, A1. So that is A1 squared times A1 squared, or A1 to the fourth, plus first row, first column, A1, A2 squared, A1 squared, A2 squared, plus A1 squared, A3 squared. This is the first element. You will have to write 9 more of the elements in order to form that D squared matrix and then compute its trace. You can, just for the trace alone, you can extend what you see here, right? For trace of D squared, I can say this is A1 4 plus A2 4 plus A3 to the fourth plus A1 A2 squared plus A2 A3 squared plus A3 A1 squared, the whole thing multiplied by 2. So I'll have to take the trace of D squared, which is half. What is trace of D squared? A1 squared plus A2 squared plus A3 squared, the whole squared, minus this A1 4 plus A2 4 plus A3 4 plus 2 times A1 lot of algebra, but even the problem says, I'm reading quote, simplify your expression as much as possible. That's what the problem says. Okay, so do this, simplify the expression. Okay. And also it asks for the eigenvalues. So I3D is nothing but determinant of D, and then compute the eigenvalues. So I'll let you try it. Okay, we're out of time today. So next lecture, I hope to wrap up this unit on tensors with tensor fields and operations, that is calculus operations. And today is 13th. My hope is we'll meet next Tuesday, which is 18th. I said the homework is due 25th, so you will have at least 1 week to work on the homework. On 20th, that is next Thursday, either I can start the next unit or we can spend that day just doing homework problems. You are welcome to ask any question. We can do like a group study. Basically, I'll help you solve some problems if you need help. So next lecture, we are completing the discussion. Next week, like a recitation session, only problem solving on homework 1. And the following Tuesday, 25th, you will submit, no extension. Okay, I'm going to be strict about it. Okay. All right, thanks so much. And I apologize for one mistake I made. I hope I'll not make such again. The spectral representation.